Bernoulli's theorem, right? I was talking about Bernoulli's theorem.
Yes, sir.
You're reading notes. You're reading, right?
Yes, sir.
You're able to follow.
Yes.
At least after the class that day, once you must read. That means make sure that you understood it. Otherwise, next day you ask me. That's what I'm telling you. Okay. Can you hear me?
Yes, sir. Yes, sir.
Now, portion for this exam over. That is solids only. Solids, that problem I gave you, last problems. Did you try all the numericals?
Yes, sir.
So 1 or 2 days I can give it just for solving numericals of that topic. If you have any doubt, you just read out the numericals from the notes. You go through the numericals. When you read, if you don't understand, you ask me how to do it. Then one day we'll finish all the numericals. Clear? Now Bernoulli's theorem. Yes. Tell me.
No, sir, nothing.
I have sent a image of that book, notebook, textbook, some numericals I have sent to you. Go through that numericals. That is very frequently asked numericals from that. So any numerical, if you don't understand, ask me how to solve it. Okay. Law number 60. 65. Which are the persons who joined right now? Roll number 5, 11, 12, 22, 23, 30, 36, 44, 45, 63, 66, 76, 78, 79, and 80, 81 absent.
Sir, one thing, sir. Sir, in the notes you sent, page number 34 is blurred.
Page number 34?
Yes, sir. The new one. Like, which starts from elasticity. While reading it, it was like 34th page is blurred.
Elasticity?
Yes, the note starts with elasticity.
Okay, it is a property of a body. Is that page?
No, sir. Page number is 34. After
No,
that,
there is no page number in this. Maybe some other book. Can you read out the topic?
No, sir. It's that page is completely blurred.
Okay. No, at least some word sentence from that you tell
me.
Before
the page before that has equation p plus that half p a constant.
Which one?
P plus PG H plus.
Previous page, you tell me, just previous page of that.
Yes, sir. The equation is P plus rho G H plus half P rho V square.
Equals P plus rho G H plus half rho V1 square.
Yes, sir.
That I'm going to just teach you right now.
Yes, sir. That page is blurred.
That
Bernoulli's theorem.
That
Bernoulli's theorem also.
Bernoulli's theorem just now I'm going to teach you.
Okay, sir.
Okay, now look. Now if you want, you can write a note also, no problem. See, this is now a pipe of varying area of cross section. Here this is segment A, segment B. Here the pressure exerted is P, P1, area A1, velocity V1. Here the pressure exerted P2, area A2, velocity V2. First we can write work done per second. Work done per second. Work done per second. At A by the liquid. Work done, on the liquid. Work done per second on the liquid. There we are pushing, imagine. So WA. Work done means force into displacement per second. So we can say WA is equal to forces pressure into area. That means P1 into A1. P1 into A1 into then into displacement per second. That means velocity V1. Now next one, work done by the liquid per second. WB. Again, force into displacement per second. Force is P2A2 V2. P2A2 force here. Displacement per second is velocity at that point, V2. Now we can say WA minus WB. P1A1 V1 minus P2A2 V2. For a streamlined flow, we know A1 V1 is equal to A2 V2 is equal to AV. This is equal to capital V, volume flowing per second. Volume flowing per second. Volume of the liquid flowing per second. So A is area, V is the velocity, capital V is volume flowing per second. This is based on equation of continuity. Yesterday I told you that. Then this we can written WA minus WB is equal to P1 minus P2 into A1 V1 A2 V2 AV, right? So we can take it as common AV. That can also be written as P1 minus P2 into V, capital V. This is equation number 1. Now look, according to work energy theorem, difference in work or how much work you're doing, that work will convert into either potential energy or change in kinetic energy or sum of change in potential energy plus change in kinetic energy. So that's what we are going to do now. So here, WA minus WB is nothing but very simple concept, this one, okay? By work energy theorem, see here, work done, P1 minus P2 into V, C equal to change in potential energy first. Change in potential energy means this is at a height H2. Then I forgot to mark. From the ground, we have to take this height as H2. From surface, if you're taking this height H2 and this height H1, okay? H2 and H1. So we can write here P1 minus P2 into V. That means work done, change in work done between A and B is equal to final potential energy is mgH2 here, mgH2 minus mgH1. So this will give you change in potential energy plus change in kinetic energy. Final kinetic energy is half m V2 squared minus half m V1 squared, because mass flowing is same everywhere. It is streamlined flow. So very simple. Sum of change in potential energy plus sum of change in kinetic energy. If it is exactly vertically increasing, only first component will come. Horizontally going, only change in velocity will come. In an inclined plane, it will have both change in potential energy and change in kinetic energy. That's what we are writing like that. Clear? Now you see, throughout divide by V, this capital V. Then this will come P1 minus P2 is equal to, here it is mass by volume, right? Everywhere we are dividing by V. Everywhere divide by V. So mass by volume is equal to density. So here we can write P1 minus P2 is equal to rho GH1 H2 minus rho GH1 plus half rho V2 squared. Rho means density minus half rho V1 squared. Now all the term indicated 1 will go to one side. P1 plus rho GH1, see this one, plus half rho V1 squared, all came to one side. Then P2 right side I'm bringing, P2 plus rho GH2 plus rho GH2 plus half rho V2 squared. You see, that means sum of pressure energy, it's called pressure energy, potential energy, and the kinetic energy per unit volume. We divided it by unit volume. That's a mass change into density. Remains constant everywhere in the flow. See, when I'm reaching to the point B, pressure become P2 plus rho GH2 plus half rho V2 squared. That means sum of pressure energy, potential energy plus kinetic energy per unit volume of the liquid remains constant. So here law of conservation of energy is proved. Total energy remain same everywhere. So this is applicable per unit volume of the liquid throughout the flow. And flow should be streamlined flow. This is known as Bernoulli's theorem. This statement is known as Bernoulli's theorem. What is Bernoulli's theorem? Sum of pressure energy, potential energy, kinetic energy per unit volume at every point in a liquid or fluid in a streamlined flow or ideal fluid, we can say. Ideal fluid, that's better. Instead of streamlined flow, ideal fluid. Sum of potential energy, kinetic energy and pressure energy per unit volume of a liquid at every point throughout the flow of an ideal fluid remains constant. This obeys law of conservation of energy, because when pressure energy increasing, potential energy may decrease. This potential energy and pressure energy decreasing, kinetic energy will increase. Total energy always remains same. So in general, we can say pressure energy, rho GH, potential energy plus kinetic energy, rho indicating per unit volume, mass per unit volume, is equal to a constant throughout the streamlined flow or throughout the flow of a ideal fluid. Is it clear?
Yes, sir.
Yes, sir.
This page only missing, right? Now, one more modification is there in the formula. Some books you can see everywhere divided by rho G. Rho G. So this equation is sometimes represented this way also. Okay. So that is P by rho G plus here only H plus here rho will cancel, then half V squared by G is equal to constant. This way also this formula sometimes represented. Then this is called pressure head, potential head, then kinetic head. Sometimes they will ask you to calculate only kinetic head of the liquid, then half V squared by G only have to take. Potential head at this particular point B means H outright. Pressure head means P by rho G have to take at that point. This is basically Bernoulli's theorem. And this page is not clear to you, isn't it?
Yes, sir.
Yes,
All
sir.
other pages are clear.
Yes, sir.
Yes, sir.
Okay.
ഹലോ അനു ഒരു ക്ലാസ് അല്ലേ നടന്നുകൊണ്ടിരിക്കുകയാണ് ഞാൻ ക്ലാസ്സിന് മുമ്പ് അനുവിനെ വിളിച്ചതേ
Okay, so this is Bernoulli's theorem. Okay, now applications of Bernoulli's theorem is there. Application. So this statement is very, very, very important. Okay, next application. First one, aerolift, aeroplanes and all. See, in aeroplane, if you're taking the side view, see a bird wing. If you're taking a bird wing, wing of the bird, it is just like convex shape. Similarly, aeroplane, if it is, this is the aeroplane, wing will come like this, right? So for this wing, this upper side, that side only I'm drawing here. Cross section of the wing of the aeroplane. It will be like this actually. Upper side will be convex, lower side is concave. You won't see that big because convex shape only you won't see that much because width is very, very large. So that variation you won't notice that much. Even here there is a flap that they can move up and down. You might have observed it in the flight. So that makes this flow more convex. So here the advantage, when this flight is moving with this wing like this, it's moving. Above the air will move faster. Below the air will go slower. So according to Bernoulli's theorem, pressure energy, okay, then rho GH, potential energy plus kinetic energy is equal to a constant. That means if you consider the airflow above the wing, V1 is faster. V1 is greater than V2. V2 is velocity of the lower portion, velocity. Any doubt?
No.
No, sir.
Because if the object is exactly spherical shape, if it is moving like this, then here and here same velocity will come. But here if it is projected, this air has to travel more distance here. Because object is suddenly moving together. So this region of the air should come back this side, right? Because when ball is moving, air will be displaced. Because if I am moving forward, where the place I am entering, that air it will move back to the place where I was occupying before. Isn't it?
Yes, sir.
So when this ball is moving here, air of this region should go the same place here. So here, if it is exactly sphere, both side air can go same speed. But if this is a shape, here it will go faster, here it will go slower. Is it clear? So in that case,
Yes,
what
sir.
happens? According to Bernoulli's theorem, look, well, this is V1, down is V2.
Sir, I'm sorry to interrupt that. My network connection was gone.
Oh, no problem. Okay. Now here upper velocity is V1, lower velocity is V2. Which velocity will be higher here?
V1.
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 Now we are applying Bernoulli's theorem to upper layer flow and lower layer flow separately. Here when we are considering V1 is greater than V2. When V is greater than V2, when velocity is high, their pressure will be low because total value should be constant. Because flight is going in a horizontal mode, isn't it? So height remains same. So when velocity increases, for that air, pressure should reduce. Any doubt?
No, sir.
No, sir.
So here what happened? Here we can say P1. Here it is P2. When V1 is greater than V2, P1 will be less than P2. Agreed?
Yes, sir.
Yes,
now
sir.
downward pressure will be high. So what happened? Air from the down start pulling upward because air always pushing onto the surface, right? So this pressure will go here. That is delta P. Delta P means what? P2 minus P1. P2 minus P1 is equal to delta P. That delta P into area will act as thrust. That thrust only lifting the aeroplane. So some people, they used to say this aeroplane, when we watch very far, looks stationary. And even we know some people, they say it's stationary. It can never be stationary. There are flights like that. Some fighter planes are there that they provide downward pressure by air flow, then keeping it opposite force. But these ordinary aeroplanes, passenger flights and all, they don't stop anywhere. That's because of relative velocity we feel. So when flight is moving above the air, that's what once, Emirates flight enter into vacuum. A large vacuum was there. Usually it is there, small gutter like thing. Air vacuum is known as air gutters. Like in road, there is gutter. In air, there are regions, there is no air. So vacuum will form. If flight entering into that, that's what jerking. Because there is pressure difference will come. Once an Emirate flight, I think 6-7 years back, very big vacuum, it entered. So naturally, there is no pressure difference. It was around 3,000, 4,000 feet, it fell down. Freely falling. Then the people inside got lifted because weightlessness, their head hit onto the top. So these all, we are studying this theory. That's what, when flight is not in the, if you're not using, washroom or any other purpose, keep always your seat fastened. That's a safety measure. Always they are announcing. Because anytime it can happen, the flight will jump into this kind of gutter. Clear? So anyway, so this is the idea of it. So when flight is moving forward, the pressure, velocity of the air above the wing is higher than velocity of the air below the wing. Therefore, pressure above the wing less than pressure below the wing by Bernoulli's theorem. Then what happened? Downward pressure is more, pressure difference acting down to up. That pressure into area of the wing, that is the upthrust. That's what you can see when flight is taking off, very fast they go. This time they adjust this one. You see, these wings they adjust because they are making the pressure difference. When obstruction comes, air will move opposite to that, above that. Air cannot stop there because when flight is moving, air has to flow back. So that's what, if convex shape is not sufficient, they are using this one at the time of flying. So air will go above this. So their pressure will be reduced. So downward pressure will increase. That's why lifting it. Until now, you didn't know this theory. So you're very comfortable in the flight. This time, next time when you travel, you will have a fear inside. Because we know the theory, especially those who are sitting near the wings, we remember about it. Because around 500 passengers or 300, 400 passengers, some flights are very big. And their luggages, the weight of the flight, how this pressure difference lift this, that's how the technology work, you just imagine. Birds are all very light.
Sir, that's
But
why
this is such a
So,
heavy
sir, what
flight.
the engines do, sir?
they provide thrust.
Moving forward. That is linear engine. What they do, that's a turbojet. Okay, so inside the turbojet, there's a fuel, just like diesel engine of a car. Okay, fuel is burning. For burning, it require air. So this air with the fan, it absorbs from the front side and burns it, pushing back side. So that act like a jet. That's it's going forward, because when turbine move forward, always it is pushing air from front. So their pressure is less than back. So that keep moving forward.
That's why we can see the wings flexing while taking off.
That's what you can see, that slowly they bend it like that. Clear? Then even at the time of landing also, speed they adjust. When speed is reduced, pressure difference will reduce. So because of the flight weight, it will come down. So this is a main technology working out of it. This is based on ideal fluid, I'm telling you. So this is only basic, fundamental. So when you go for aerodynamics, that this one, aeronautical engineering and all, they will give you, if air pressure is different, all this thing, viscosity, everything will come into, then formula will be very complicated then. There are advanced formulas you have to go. But this is the basic. From here only all modification come. Is it clear?
Yes.
Yes.
So this is one of the main application, aero lift. They can ask the aero lift or lifting of the flight based on which principle? Pascal law, Bernoulli's theorem, Torricelli theorem, like that, so many theorem they'll give. Newton's law, like that. So this is Bernoulli's theorem. Clear?
Yes.
Next one, your cricket, spinning ball. You see that spin ball you throw, right? It's a technique in cricket to confuse the person who is batting.
Yes, sir.
So what they do, there are two types of spins. One spin, clockwise spin, another anti-clockwise spin. First, I will tell you, without spin, what will happen? See, suppose when you throw this ball, it will go as a projectile. Its center of gravity will moving through this line. So the person who bats here can expect this ball will reach here, he will hit it. Isn't it? But suddenly, without expecting, this man may be expecting you are throwing it this way, but suddenly you give a spin. So for example, anti-clockwise spin you are giving to it, anti-clockwise. So remember, once again, when this is going in horizontal direction, velocity here and velocity here, airflow. Ball velocity is V. When ball is moving with the velocity V, air will be moving back with the same velocity, right?
Yeah.
Suppose you run with the velocity V, air also going back with the same velocity. Am I right?
Yes, sir.
So normal condition, this is a normal velocity. When the ball moves straight line, just ordinary throw, this is the velocity of the airflow. But if you give a spin, now you're going to give a spin. Ball is going to spin anti-clockwise. This time, air in contact with the ball also will rotate with the same speed of the ball, right? Viscosity.
Yes.
When we take any rod, keep in water, rotate it. Water layer in contact with this rod will rotate faster, right?
Yes, sir.
Water layer which is far will go slower. So here also, when this is spinning, air layer which is in contact with this ball will also spin like this. So this is the air layer due to the spin. Air layer, okay? So that's called spin velocity. This also spin velocity. This time you see, this velocity and this velocity will be added. Sorry. It will be added. This will be subtracted because this velocity in this direction, spin velocity opposite. So here it will come V minus Vs. See blue color line this side, red color line opposite. Here both are in same direction. So V plus Vs. This will be added. Any doubt?
No, sir.
No, sir.
So this velocity above the ball is higher than velocity below the ball. Agreed?
Yes, sir.
Sir.
By Bernoulli's theorem, velocity is high means pressure low here. Here pressure high. Now this ball will get a upward push. So this person expecting ball will come this way, but this ball will go this way and hit here. Suddenly that path will change. This effect is known as Magnus effect. Magnus effect. In football also they are doing the same technique. Before that, this one. Clockwise spin if you are giving, just reverse will happen. Above pressure will be high, below, above pressure will be high, below low. Then from top to down it hit. Then ball will go down to the actual path. So both path will confuse him. He is expecting ball comes this way. So depends on clockwise spin and anti-clockwise spin, that ball changes the path. This is Magnus effect. Even football. Nowadays, the people are practicing like that. See, if this is the goal post, from exactly 90 degrees, they will hit the ball. You can see this ball will come and enter into the goal post.
Banana.
Banana cut. That's mainly what's happening. This ball, this side, while hitting, you need practice. While hitting, one side, they will give more force. So that means torque, they will give. One end, if it's hitting, force into perpendicular distance, will give a torque. So this physical education is almost physics only. So it will rotate. So while this is moving, one side pressure will be high, other side pressure will be low. So this will go and enter into the goal post. This is all very commonly they are using now in sports and all. Clear? So this is we call Magnus effect. Next one, atomizer. Atomizer means your sprayer and all. For example, a simple method I will show you. See, here there is a liquid inside here. Here there is a very narrow tube. This is the barrel, like a cylinder. This end is very sharp, small opening here. Here, there is a piston. Now, when they push the piston, air will flow here. So velocity increases, here pressure decreases. Velocity increases inside, pressure decreases. So from here, atmospheric pressure is more, that pushes the fluid here. So that will be sprayed out. This way perfume and everything is working. When you're pressing, then what happened? That area pressure is reduced, liquid will come there and that will be sprayed out. Is it clear?
Yes, sir.
Yes, sir.
This is atomizer. The next one, venturimeter. Venturimeter means it is a device used to find flow of liquid per second. For that, there is a device like this. See this one? Here, this is A1, this is velocity V1. This is the point A. This point B, this is A2, V2. Again here, A1, V1, same area here. Okay, this is again A1, V1. Now here there is a small pipe you can see. Here also there's a small pipe you can see. Water flow from high pressure to low pressure only. So why this pipe is kept here? Since pressure is more, here water level will come up this much. Here it will be little less. If you're doubtful, you can see in a garden, see this is a water tap. There's a pipe going like this, okay? If there is a puncture here and here and here, here you can see water splash more high, here less high, isn't it? What is the reason? Pressure must be, here pressure must be more than this point. This pressure must be more than this point. Then only water will flow. Otherwise, water cannot flow. Water always flow from high pressure to low pressure. Clear? So if
Yes,
you can
sir.
measure this height, that will give you H rho G, height, density, gravity, pressure of this column will get. That pressure is exerted from here. So this height difference, you see, this height difference will give you. Now, here, this much only water can be lifted. Here, this much it can be lifted. This difference in height between this is X, this is X, this is Y. X minus Y will give you H. So H rho G will give you pressure difference of these 2 points. Clear? Once we
Yes.
can calculate pressure difference, there's a formula here. V is equal to A1, A2 into root of 2GH divided by A1 squared minus A2 squared. No need of derivation, just by heart. H means this is the way we calculate H, pressure, this difference in height. Then this will give you rate of flow of liquid through this pipe in 1 second. Any doubt?
No, sir.
Next heading, velocity of efflux. Velocity of efflux. That means suppose this is a very big container, very large container. You can see a dam, very big dams, reservoir. There is water level up to here. Okay. So here, water, here there's a small height, small hole. From here, water splashes out, you can see. See from here, this small area opening, small area. Through here, water will splash out.
Yes.
Velocity of this water comes out. This small orifice is known as velocity of efflux. Here I'm marking it V2. When this is coming down, here water level will come down, right?
Yes, till that level.
So here we can write here pressure initially P1, A1, V1. A1 means area of the surface. So P1, A1, V1. So P1 here we can say equal to atmospheric pressure. Here pressure exerting is atmospheric pressure only.
Yes, sir.
Here pressure exerting is atmospheric pressure actually. So here I can mark PA. Area we can calculate, say A1. V1 I'm marking, yeah, V1. Finish it. Now this goes down. Here pressure again atmospheric pressure, that is P2 is equal to P. Velocity V2, area A2. Is it clear?
Yes, sir.
But you can see here water splashes very fast. But here that layer comes very slow, isn't it?
Yes, sir.
Big,
Yes.
See, suppose the dam has very big reservoir. One side on the wall, there's a small hole. There you can see water splashes very high velocity. But will the water level of the dam come down fast?
No.
That go very small. So we can say V1 is very, very smaller than V2.